Ensuring the safety of autonomous driving systems is a critical challenge that requires reliable on-time prediction, especially in emergency scenarios. However, these emergency situations are long-tailed and hard to collect, which restricts the ability of current systems to make accurate predictions. To address this problem, we have developed a new dataset and novel techniques to enhance the performance of motion prediction models in complex, time-sensitive driving situations. At the core of our work is the ESP dataset. But what makes this dataset so important? Let's dive into a real emergency scenario. A sedan dangerously cuts in front of our autonomous driving truck on the highway. Human drivers could reasonably predict this dangerous cutting. First, a high-speed sedan approaching a slow truck suggests the potential for lane change. Secondly, since the left lane of the sedan is always clear, the left lane change behavior for the sedan tends not to happen, as it can be done at any time earlier with lower risk. Moreover, there is an off-ramp exit within 200 meters, which might force the sedan to cut into the rightmost lane to make the exit. Now, let's have a view of the full replay of this dangerous scenario. And the sedan did make a risky cutting. All these considerations boil down to semantic environment information. In this context, we refer to them as extro-spective cues, which means the observation of external things. However, state-of-the-art models for motion prediction, such as MTR, tends to focus on introspective cues, including historical states and map polylines, while overlooking these extrospective cues. The ESP dataset covers over 2,100 kilometers of highway driving, featuring diverse and challenging scenarios. These include a wide range of traffic interactions, such as merges, lane changes, ramp outs, and cut-ins. Importantly, the dataset contains a high density of aggressive driving behaviors, which are often the most critical and difficult to predict. In addition to the detailed trajectory data, the ESP dataset includes the comprehensive semantic information about the driving environment. This includes the location of speed monitoring systems, junctions, and other real-world objects that can provide important contextual cues for predicting future behavior. Furthermore, within the realm of extrospective cues, we are concerned with interactive factors like time to collision, distance, and speed differences. By incorporating all these extrospective cues, we have created the ESP dataset. When combined with our proposed simple ESP encoder, these extrospective cues can be absorbed by the state-of-the-art models. While existing prediction metrics, such as final displacement error, FDE, and average displacement error, ADE, provide useful insights, they are still limited in their ability to capture the time-sensitive aspects of emergency scenarios. As we can see in this figure, trajectory A and B are not distinguishable from the ground truth in terms of ADE and FDE. However, the cutting moment for these three trajectories varies significantly. This level of temporal accuracy is often the difference between a successful intervention and a catastrophic collision. To address the limitation of the current metrics, we proposed a new metric called the clamped temporal error, or CTE. The mean CTE metric is designed to give a clearer picture of how well a prediction model can anticipate the precise timing of dangerous cutting, which is essential for the safety of autonomous vehicles. Our experiments with the TNT and MTR models have shown that incorporating the ESP encoder can consistently improve their performance, underscoring its effectiveness. One more interesting application is that our ESP features can be described in natural language, and we have already integrated it into large language models, such as GPT based on long chain. GPT initiates with the Get Vehicle Ahead TV tool and receives an observation indicating the presence of a small vehicle ahead of the target vehicle. Following further inferences, the model ultimately predicts the cutting intention of the target vehicle in advance. In summary, by incorporating the currently ignored extrospective cues, we can improve the performance of prediction models. And the timing aspect of emergency scenarios should be further concerned by benchmarking metrics.